It is Kevin. Yes, sir. Great. Hey, Kevin. What'd you do to, like, I don't know, get that answer? How? So you did A times C, and you got, what, negative 40? And then what'd you do? Good. So what'd you get there? Good. And then what'd you do? Bridget, you're on deck, by the way. There you go. Now you're on a roll. Then what do you do? Uh-huh. Okay. Yeah, so the x minus 4 is the magic binomial that repeats itself, so that gives you this part right here. And then what's left over, yeah, 2x and 5 is that piece right there. So, alrighty, way to hang with it. Did anybody do it a different way? A little shorter, a little guess and check maybe. I'll show you a shorter way. If you like it, use it. If not, you can bag it. Do you see how 2? That's a prime number. It's actually really important for today's lesson, the difference between prime and composite. 2 is what we call a prime number. It's only divisible by 1 in itself. You could actually use guess and check to get through this problem pretty easily as well. You know that in factoring these trinomials where the degree is 2, our mission is to kind of stuff these 2 sets of parentheses. So I can ask myself, you know, hey, what multiplies to give me 2x squared? Well, 2x times x gives you 2x squared. That's not too bad. And then I'm looking at it and I'm like, oh, well, what are some factors then of negative 20? So factors of negative 20, like I always think about, you know, like 4 and 5, you know? So I know 4 is going to go in one of the sets of parentheses and then 5 has to go in the other. By the way, it's guessing and checking. If you were to pick 2 and 10, it wouldn't work out for you. But I just happened to pick 4 and 5, and that's actually part of my answer. So if I pick 4 and 5, I'm like, oh, you know, like that multiplies to give me 20. So I would play around with those numbers a little bit and maybe put the 5 here and the 4 here. And then I'd be like, oh, you know, 10x and 4x, it's never going to give me that 3x, so that doesn't work. So I'd maybe reverse it. I would put the 5 here and the 4 here. And I'd get 8x and 5x. And I'm like, oh, you know, that works. I could make that happen, you know. If I just make the 8x positive, but the, I'm sorry, if I make the 8x negative, but the 5x positive, I'll get that negative 3x in between. So you could guess and check your way out of it. Might be quicker. You all right with that over there? Yeah, okay. It's another option. If you don't like it, bag it, you know. This will be faster for you in the end. You're going to factor like a million times in chapter 8, so figure I'll show you some faster ways besides AC grouping. Okay, Bridget, you were next, dear. Yeah. How'd you get that, Bridget? Yeah, very good. You use our square root method on that one. And then we have Haley. Good girl. How'd you do it?
I saw that the 9 would be square rooted and like the x too, so like 3x times 3x would be 9x squared, and then like plus 1 times minus 1, negative 1 is like negative 1.
Yeah, and the outers and inners go away, so that's nice too. Hey, Gio, what'd you get for the last one? What'd you do? You could do C as 0. You could. I think that's longer though. The method we do is our book calls it the common monomial factor. We call that the greatest common factor method. So you have to take out what they have in common. So Gio, what do 8x squared and 20x have in common? Yeah. And then you just kind of use your distributive property in reverse. So you ask yourself 4x times what gets you back to 8x squared, Gio? Mm-hmm. And positive 5 will get you back to 20x. So, yeah, that's it. Did you make that more complicated than it had to be? Questions about that? Because if those methods are rusty, this lesson gets to be rough. Okay, so today our overarching goal is to give you another sort of row to add to this chart. We're going to give you another type of problem to factor. Those problems include perfect cubes. But before I get too far into that, I wanted to address with you, what your final answers when you're done with all of this stuff, like what it should look like. Now, this has come up a couple of times so far in our lessons together where I say to you, your answer isn't factored completely. For some of you, I was just looking at your homework while you were doing the warm-up a little bit. It happened on number 11 in the homework last night. Number 11, you had to take out a GCF of 3. Some of you forgot to do that, so your answer wasn't factored completely. Some of you are looking at me like, what? So let me just give you another answer. Another case where this came up. Do you remember this from Friday? It's like your little factoring checkup. A couple of you got number 1 wrong because you forgot to take out the 16 to start off with. Why you have to do that, just to remind you, is that is part of what it means to factor completely. So let's maybe just review those definitions to start off with today. When a polynomial is factored completely, we can actually say that it's prime. So in order to understand what it means for something to be factored completely, we should probably develop our understanding a little bit of what it means to be prime. And to develop your understanding of prime polynomials, I need to go back to your understanding of prime numbers. Yes, prime numbers. So yeah, does anybody have a definition of prime numbers? What that means? But 1 in itself. I'm glad that you added that onto your definition. Very good, Bailey. You're right. They're numbers that aren't divisible by anything but 1 in itself. So Bailey gave us a pretty decent definition. Can anybody give me some examples? 13. 1 is not prime. It is special, is what we call it. That's just it. It's too special to actually be prime. Prime is not. Or prime. 1 is not composite and it's not prime. It's actually neither. But it does come up a lot. 1 is just far too special to be prime. So that's how you could remember that. It's kind of like 0 is sign neutral. It's not positive, it's not negative. 1 isn't prime and it's not composite. It's neither. 11, very good. 23. I heard a couple. Anybody say 2? Yeah, 2. That's our only even prime number, in case you were curious. Is everybody okay if I move on from prime numbers? Okay, sounds like you get it. Thanks, Kevin. So prime polynomials are just like prime numbers with respect to the fact that the only thing they're divisible by are 1 and itself. Please remember that we could always, in addition to using that definition, that was Bailey's definition, prime numbers are numbers that are only divisible by 1 in itself, we could say that they're also not allowed to be composite numbers either, like 6. 6 has factors of 1, 2, 3, and 6. Or 12 has factors 1, 2, 3, 4, 6, and 12. So they can't have lots and lots of factors, right? Well, same thing here. A prime polynomial is a polynomial with two or more terms. It's going to be prime if it cannot be written as a product of polynomials of a lesser degree using only integer coefficients and constants. I'll show you what that means. It's a mouthful right there. Here's what that means. Do you see 16x squared minus 4x plus 8? That is not factored completely. So it is not a prime polynomial because 4 is a common factor in every single one of its terms. So what we're saying when we factor completely is what we're saying is write an equivalent expression for your original polynomial, but write it as a product of prime polynomials. Very alliterative, product of prime polynomials. That's what it means to factor completely. In addition, you might look down here. There's another example. See, x plus 2 equals x squared minus 5x plus 6. That is not factored completely because this guy right here is not a prime polynomial. A prime polynomial would be x plus 2 because I can't take anything else out of it. But x squared minus 5x plus 6 can actually be rewritten as x minus 3 times x minus 2. So to take this guy and write it in completely factored form, we would write that as x plus 2 times x minus 3 times x minus 2. That is factored completely. And all of these factors are prime. I can't take a greatest common factor out. I can't use my difference of two squares formula again. That is all factored completely. All right. Here's your new... Ooh, what's up, Alec? Okay. So if you take a look at these examples here, you're going to notice the titles of the formulas are there. We're going to factor today a sum of 2 cubes and a difference of 2 cubes. What do those phrases have in common? You see it? They have the word cubes in common. We can't use these formulas unless there are perfect cubes in them. So we should probably make a list of some perfect cubes real quick before we go too far into this thing. Perfect cubes. Anybody know some? 8. Yes. Because 2 times 2 times 2, or 2 to the 3rd power, would give us 8. Geo. 27. Because 3 times 3 times 3. 4, 3 cubed. I hear it, Kevin. 125. Not the one I heard, but yes. 64 is the one I keep hearing. You forgot one. 1, yes. 1, though it's not prime, is a perfect cube because 1 times 1 times 1 is 1. 1 to the 3rd power is 1, so 1 is a perfect cube. Those are the numbers you're going to see. Variables you're going to see are like x cubed or z cubed, or, you know, we could do like 8x cubed, you know, combination of the two. So these are going to be the things, the terms in your polynomial, and you're going to have to factor. Please notice you must memorize these formulas. And then I have a little mnemonic device here, SOAP. SOAP refers to the signs in your parentheses. I'll talk a little bit more about SOAP in a second. Okay. So for instance, sum of 2 cubes. The first thing you want to do is decide, does this fit the description? Does this problem fit the description for being a sum of 2 perfect cubes? Well, check it out. X cubed is a perfect cube. Oh yeah, and 8 is a perfect cube. Those were things in my list of perfect cubes that I made up top. So this problem fits the criterion for using the sum formula, or the formula for the sum of 2 cubes. To use the formula, it's helpful to identify an A value and a B value. A is just the cube root of your first part. B is just the cube root of your last part. So the first part is the first term. The cube root of x cubed will help me determine A. To determine B, you have to take the cube root of 8. So you take the cube root of your first part, cube root of your last part. You've done this before with the square root method. You took the square root of the first part, square root of the last part. Now we're doing cubes. So cube root of the first part, cube root of the last part. Cube root of x cubed. X, very good. Cube root of 8. 2, very good. The first set of parentheses is always, for this formula, A plus B. So do you see how I have A plus B in my parentheses because A was x, B was 2? So this is x plus 2. To get the trinomial, in the back part of the formula, you square the first part, A. So A squared would be x squared. You square your value of B, which is 4. And then you multiply the two things together. That's 2x. The tricky part of the formula sometimes resides in memorizing the signs, and that's where SOAP comes into play. SOAP is just a mnemonic device to help you remember what signs go where. SOAP stands for same, opposite, always positive. Same, opposite, always positive. You see that? Spell SOAP. Same, opposite, always positive. So what that means is that the first symbol in my parentheses is the same as the symbol in the original problem. So I just recycle that. The second sign in the problem is the opposite of the first one I wrote. So this one starts with a plus, which means my second symbol is a minus. And then the third one is always positive. Difference of two cubes works the same way. You first want to decide if you should use the formula. What's up, Alec? Yeah, you have to square the value of B.
Okay.
I just used the formula.
Okay.
Does that help you out? For real, for real? Okay. For real, for real. So what I'm going to go ahead and do right now is decide, should I use my formulas? And, well, hey, they're under the example, so I should use the formula. Now, there's more to it than that. You'll see that I have 8x cubed. Right, we listed that out as a perfect cube earlier. Oh, yeah, and we listed out 1 as a perfect cube. So I could use my formulas, right? After I decide that I can use the formulas include A and B. So I need to calculate A and I need to calculate B. A is found by taking the cube root of your first term. B is found by taking the cube root of your second term. First term was 8x cubed. Second term was 1. The cube root of 8x cubed, 2x. Cube root of 1, that's 1. And now I just substitute those A's and B's into our formula. So you see our first set of parentheses says A minus B. So that's how I got 2x minus 1. You just subtract your A minus your B. To get the trinomial on the back, you square A, because it says A squared in our formula. A squared is going to be 2x times 2x. That's 4x squared. I would square the value of B next. 1 times 1 is 1. And then I multiply A and B together. 2x times 1 is 2x. And then I do my same, opposite, always positive. So this symbol in here is the same as my original. The next symbol should be the opposite of that one, and the last one is always positive. And that's done. The trinomial at the very end, never factorable. You can't use AC grouping on 4x squared plus 2x plus 1. If you want to, you can try, but it's never going to factor. This is prime, and it's factored completely. I thought I saw a hand somewhere. Oh, there it is. The formula takes care of that. You don't have to look at the signs. That SOAP thing takes care of the signs for us, Danielle. Any other questions? Okay, so now you get to try. Try not to peek at the formulas, but if you have to, you have to, right? Do what you need to do. I'm going to go ahead and give you a moment to try those. Sorry, Mr. Crater's announcement took a little bit of time there, huh? You just want to go ahead and make sure your independent practices are correct up here. We're going to pick up where we left off with this tomorrow. Only the first 6 problems on that worksheet are you capable of doing. So take some time to memorize your formulas, okay? That's it. Have a good night.